Welcome to our SIGMOD 2023 tutorial. In the next 20 minutes, we will give you a brief overview about data processing with FPGAs on modern architectures. My name is Wenqi. I'm a PhD student at the System Group at TTG Zurich. I will present this tutorial together with my colleague Dario and Professor Gustavo Alonso. The first question you might ask when watching this tutorial could be, why would we ever present a hardware topic in a database conference? Well, this is because computers as a general purpose technology has come to an end. And like it or not, this is the fact and the challenge that the database community must tackle in the next decades. As you can see in this figure, the CPU performance improvement is diminishing over years, and so does the performance per dollar improvement. The slow technology advances reduce the user's willingness to adopt them. Because of this, hardware vendors are less willing to invest on newer technology. This eventually makes the technology advances even slower. Some suggest that the technology involvement on CPUs may even end by 2030. So in the post-Moore's law era, what should we do? One solution is to specialize hardware design. Rather than using CPUs to do everything, we use specialized hardware that are especially good at some types of workloads. This is especially true in the cloud computing context. Due to the very large-scale workloads, we can gain a significant benefit if we can improve system efficiency by specializing hardware. In the data center, it is also easy to configure multiple types of hardware. For example, we can have 20% of servers equipped with FPGAs, 10% of server equipped with FARNIC, and 30% of server equipped with GPUs. Now, among the multiple types of hardware, why do we choose FPGAs for data management research? The reason is that FPGAs is a type of fully programmable hardware architecture. It allows us to explore different microarchitecture designs. Although GPUs are still great processors and it provides high floating point operations per second and high bandwidth, the microarchitectures of GPUs are already fixed, thus the design space is smaller for database researchers. For FPGAs, we can control the hardware architecture and observe the architecture effect on system performance. If the performance of the FPGA is promising, we can even consider to turn the accelerator into ASIC to further boost the efficiency. Due to this reason, our group has spent the last decade investigating FPGAs in the context of system research and data management workloads. We outlined the tutorial as the following. First, as we just did, is the introduction and motivation. We will then spend time on how to program FPGAs. Afterwards, we will introduce FPGA cluster that we maintain at ETH Zurich that is publicly available to academic researchers. Finally, we will introduce 3 use cases of FPGAs that our group has been conducted research on. Now, let's take a look at FPGA programming. FPGAs used to have steep learning curves. This is because developers used to write verbose and low-level hardware description languages, such as Verilog and VHDL. On the left-hand side, we show a program of HDL, and this 20 lines of code is just for a single multiply and accumulation operation. As you can probably imagine, it will be extremely time-consuming to implement any complex applications using a programming language like this. For example, if we use this multiply and accumulation module to implement a 4x4 matrix multiplication, it takes around 100 lines of code. And if we want to upgrade the matrix size from 4x4 to 5x5, we even need to rewrite the code to support such functionality. Recently, high-level synthesis, or HLS in short, has come as a rescue. It allows users to use high-level languages like C and C++ to program FPGAs in combination with some pragmas to control the hardware behavior. Studies shows that HL's tools has led to a significant shorter development cycle, although the hardware control expressiveness of HLS is still not on par with HDL yet. Here is an example using HLS to write a matrix multiplication. It is pretty similar to software coding. We just need some extra programs to indicate the hardware behaviors. Remember in the previous example, the HDL used 20 lines of code just to implement a multiply and accumulation operation. But now with HLS, using the same amount of code, we can finish implementing an entire matrix multiplication.
Okay, so one of the main barriers to doing data processing system research on modern heterogeneous systems and FPGA hardware is access to this hardware. And this is especially the case for large-scale distributed data processing applications and systems, which are actually the most prevalent in today's AI and cloud-dominated environments. So firstly, the problem is an inherent lack of good open source supporting infrastructure to build complete systems. If we take a look at modern cloud offerings by Amazon or Microsoft, they are closed source, and there is very little true system level exploration that you can do on such platforms. Secondly, the tools themselves can be quite limiting as well. They are also proprietary, and they typically offer a limited set of features which can be utilized by users. And in many cases, this can limit the amount of design choices these users can make. Fortunately, things are starting to change, and we are seeing more and more open source infrastructure being available. And in this section of the talk, we are going to cover one such infrastructure that we manage at ETH. It's built on top of HAC, which stands for Heterogeneous Accelerated Compute Cluster, which was donated to us by AMD. And the goal of this AMD initiative is to support system research in adaptive computing, especially in the context of a data center and cloud. We're going to show the hardware organization and the software tools that we use and that we have developed for this cluster. We're also going to spend some time showing how we manage external access to this cluster and the tools that the management tools that we developed for these purposes, by presenting a workflow that automates the booking, installation, and deployment on these servers. Now, from a hardware standpoint, the cluster contains various compute resources which can be freely exploited. It contains a number of different powerful Alveo accelerator cards, including some novel architectures like Versal, which contain hardened AI logic for ML-oriented workloads. And importantly, all of the nodes in the cluster are connected via high-performance 100G network, which can be used to develop smart NICs and large-scale distributed applications. We're also going to show the software abstractions that we created to leverage this hardware and make the most of its potential. Now, as I mentioned, state-of-the-art vendor tools are in some cases not sufficient for system-level research. And so for this reason, we have different usage flows, including the bare metal flow, which exposes the low-level interfaces to the underlying hardware. And for these purposes, we have shells like Coyote and Ancien, which we developed within our group. And importantly, these shells also provide the necessary networking abstractions like RDMA and TCP/IP stacks, which can be used for these large-scale distributed applications. Okay, so as a first use case, we have selected one based on conventional database architectures and the impact cloud designs had on them. The use case is based on Farview, which is a project we've done in collaboration with HP. Farview is a platform designed to explore disaggregated memory research for modern database systems. So what is the motivation for Farview? Well, one of the main bottlenecks modern databases face is I/O overheads. And although we do have faster storage today with SSDs, NVMEs, I/O overheads still remain one of the major factors in the overall performance. And so what modern databases tend to do to minimize these overheads is they tend to keep more and more data in local DRAM in the compute nodes. And this approach has two major drawbacks. So first, it induces excessive data movement. So query optimizers will typically try to push down certain operations like projections or selections, which will often filter out large portions of the data. And even though this is the case, in traditional systems, data still has to be shipped all the way to the compute nodes and then processed there fully. This additional data movement has a direct negative impact on the overall performance. Secondly, memory capacity is another limitation. So DRAM is expensive, and provisioning it for every compute node independently can be quite costly. So for similar problems, there is a tendency in modern cloud environments towards disaggregation of compute and storage. So what we propose in Farview is to further disaggregate compute and memory as well. And this is something that is quite a trending topic currently, with research being done in both academia, but also in industry with systems like Amazon Aqua, which tried similar things. So from an architecture standpoint, Farview is an FPGA-based SmartNIC, making DRAM available as a pool of network-attached memory accessible over high-performance RDMA network. One key feature of Farview is the capability to offload operators and to perform line rate data processing with minimal added overheads. So from a database perspective, Farview acts as a disaggregated buffer cache with operator pushdown capabilities that is byte addressable by the threads running queries in the compute nodes. So Farview is positioned to address these issues of inefficient data movement and memory capacity limitations by offloading certain portions of the query processing and by provisioning the memory on demand on these remote nodes. So as an example, here we have two queries, and in traditional systems, all of these tables would have to be moved to the compute nodes. What we do in Farview is we offload these projection and selection operators directly to the remote Farview nodes and perform the processing there. Now, importantly, this processing is done simultaneously with the data being read from the memory and being sent to the network. So this processing is very nicely hidden behind these other operations, and thus the overheads, the added overheads of this processing are negligible. And all of the current operators in Farview are implemented in the same fashion.
The next use case we will present in the tutorial is Approximate nearest neighbor search, or ANN search. ANN search has become the backbone of many AI systems. Given a dataset of a number of vectors and a query vector, an ANN search tries to find out the most similar vectors from the datasets and return them to the user. For example, search engines such as Google and Bing use ANN search for web document retrieval. The web documents are encoded as vectors and stored in a database. When a user's text query arrives, the text is also encoded as vector to issue an ANN search to retrieve relevant documents from the database. Similarly, recommender systems encode contents such as advertisements or videos as vectors and store them in the database. And then they use the user's profile as the query vector to retrieve some candidates from the database that the user might eventually be interested in. Recently, natural language processing community even use ANN search to improve language quality. For example, they can couple a large language model with a document database and retrieve the documents based on the language context. In this way, they can improve the language generation quality a lot. There are existing CPU and GPU-based vector search systems. For CPU-based systems, the performance is restricted because of the CPU microarchitecture. They are very slow in evaluating distances between query and quantized database vectors. GPU systems, although faster in this dequantization step, they are extremely costly for large-scale deployments. For example, given a database of more than a terabyte of vectors, we need more than dozens of GPUs in order to serve the system. Additionally, GPUs are known for their high throughput rather than low latency, yet the latency is actually critical in online ANN systems. In this tutorial, we will present Vectie, a low latency and cost-efficient vector search system. Rather than using the HBM, which is expensive and small in capacity like GPUs, we use regular DDR memory, and we can use a bunch of DDR memory to easily support large-scale workloads without having high cost. We then use FPGAs as a near memory processor close to the memory. The FPGAs can decode the quantized vectors at line rate and handle the query processing in a flash pattern. We have a number of these accelerated memory nodes sitting on the network. We also have a CPU node that handles queries coming from the users and dispatch the queries to the FPGAs based on the index. The final use case we will present is personalized recommender systems. These recommendation systems are everywhere, from online retail to content providers. According to Meta, over 80% of machine learning inference cycles in their data centers are devoted to recommendation filtering and ranking. Now we show an example of these deep recommendation models. Unlike DNN, which only has fully connected layers, this deep recommendation models has a unique embedding layer. And this embedding layer consists of hundreds of embedding tables. During a inference, each table is looked up at least once in order to finish the feature gathering. And because there are so many tables, we need hundreds of DRAM lookups, and these DRAM lookups are random. According to our profiling, these embedding table lookups consume more than half of the inference time. In order to solve this, we propose MicroRec, an efficient recommendation inference engine supporting high-performance embedding table lookup. We use an FPGA that consists of heterogeneous memory hierarchy in order to support such functionality. The FPGAs consist of regular DDR memory, just like CPU servers. It also consists of high bandwidth memory, and this high bandwidth memory contains multiple memory channels, and we have 32 channels in our case. Each channel can be accessed individually, and all the 32 channels can be accessed in parallel. The FPGA also has some on-chip memory, which is the SRAM, that can be accessed within a single clock cycle. The next step is that we allocate the embedding table to this heterogeneous memory hierarchy based on their sizes. After this allocation, the FPGA can then look up dozens of embedding tables within a single run, thus achieving very high embedding table lookup performance. Now we have given you an overview of the tutorial, and we look forward to seeing you at SIGMOD 2023.